And what it says, you can just go through that, but effectively what it says is that we all know that AI systems or artificial intelligence systems are invariably complex for various reasons. And they also have great capability in producing very high results of predictions. But yet we cannot explain what these predictions do or how they have arrived at. It is indeed a black box. And therefore, it would be very nice to have a tool that would kind of turn that black box into a white box. So normally we work with a lot of samples, and then the system decides its performance and it gives a global output in that sense. It's global in that it covers quite a lot of data on which it is designed. But when we look at an instance such as a test sample, then that sample has its own features, and those features are treated local. So what will be good to know is how does this particular set of features contribute to the global output of any model that has been designed. So that is what is being treated as local and global. So in this paragraph, it says we need a tool to detect the relationship between local specific features and a model's global outputs. So we do not have the resources to write such an XAI tool for each model and project we implement. So it's reinventing the wheel and repeating the process for every other model we develop. Therefore, we need what's called as the model agnostic algorithm, which can be applied to any model to detect the contribution of each feature to a prediction. So this is what XAI is all about. And I'm just going to, I'm sure some of you are already familiar with that, and some of you know about it, but not dealt with it. But I see a lot of papers on AI, so maybe they can take a little bit of a twist towards XAI. I hope this motivates you in that direction. So we are looking at touch stroke dynamics, which is basically how we use our mobile phones and how we swipe across the screens, and how often or frequently or with what pressures we apply on the surface and so on. So it's all about using that trait as a behavioral biometrics is the focus of as an application. And this piece of work has been kind of initiated and is ongoing between us as a collaborative group between the University of Hertfordshire, the University of Southampton, and the University Queen Mary University of London, all three in the UK, and a key partner, Multimedia University in Malaysia, and two partners from Gran Canaria, from the University de la Palma, from Gran Canaria. So this first of all, this collaborative relationship occurred because of the various conference networks that I had attended to or they had come over to attend to, and that kind of identified the common interest between participants, and that's how we built this network. So I'm very happy to work with these people because each one has got a unique capability to contribute to the project. For example, from the University of Southampton, they stand on the British Standards Committees on Biometrics, and Queen Mary contacts work with the National Physical Laboratory in the UK, which will help us to do benchmarking testings. Multimedia University and University of Hertfordshire jointly shared a funding whereby we could hire researchers to do some implementation. And from Gran Canaria, we had the researcher actually do a postdoctoral research with me, but he's also a staff member there. So we continue to do joint research. So that's about the partnership on this project. So let's give a little overview on XAI or explainable AI. In particular, we are going to look at applying XAI to biometrics as a broad topic, and within biometrics, touch stroke dynamics, as we can see from the figure here. So this is an emerging field, but it's not too new. There has been quite a lot of work that has been on, and it kind of removes the veil of black boxes of neural networks or deep learning architectures and provides more transparency into the layers. And you would have seen from today's morning's session, as well as from your own papers, the importance of AI in key applications such as in making business decisions, or in medical diagnosis, or investments, or making recommendations, and law and enforcement, and any more. You can keep counting how important AI is in these areas. These days, governments have realized it is not enough if we implement or use AI, that such applications must be responsible in their own rights so that we can trust their decisions and accept their decisions, but also be able to question the decisions. So there are laws, particularly the General Data Protection Regulation in the European Union is based on this, which we call as GDPR, which basically says that if any user is going to be, if his data is going to be used in an AI system, then he needs to know how and why it is being used, and they need to know how or what impact it will have on their own lives. So people are very careful about that, and therefore the need for XAI systems. So when we introduce explanations into AI systems, and when we can clearly see what is happening technically within the system, it provides transparencies, and therefore it serves different purposes for different users. Users can trust these systems, developers can have more trust in their own development, and people will be more confident in allowing AI systems to make some of their decisions. So that's the focus of XAI and the purpose as well. I'm not sure if you can see this figure very well, and I hope you can. So in a way, it is asking this question, what is expected of XAI? What do we do today, and what more is expected to come out of it? So on the top, we have a diagram, an architectural diagram, which says current AI systems take a lot of data in, which we call as the training data. They have a learning mechanism, and they will learn a function, which we see as the layers of neural networks, and then it creates a model based on the input data. At some point, we test the system with some kind of test input, as in this case, you can see on top, there is a cat which is given as input, test input to the system. And we expect the system to produce a predicted output. So it clearly says this is a cat, and the predicted probability is 0.93. So that's what current systems do. But any user who is using this system will wonder, how did the system manage to arrive at this result? Will it always give us correct results? What if the test input is something else? And then when will it fail? Can I trust it? And if there is an error within the system, how does the system manage to correct it? So there are various questions that pop up in our minds when we use such systems. So what we want to be able to build within this system is, when it's creating a model, is also to embed explanations. So if you look at the bottom architecture, we still have the same training data, but there is a new learning process. But that learning process also contains an explainable model. So the model is not a mere model, but also has embedded explanations. So we can then get an output, which is the right output, perhaps this is a cat, but it also says how it arrived at that result. It has fur, whiskers, and claws, and it has certain features. Look at the images below. Maybe it is the ear lobes, maybe it's the texture related to the ear lobes or the head portion. So this is how it arrived at this particular conclusion. Now the user is able to understand why it happened so and why not, when will it succeed, all the questions it had earlier, they may be able to find some answers to it. So this is what XAI is expected to do, and we hope to see. So there are lots of terminologies within the XAI framework. And here I'd like to introduce two terminologies. One is transparency versus explainability. So transparency deals with explaining how the model itself works, probably which neurons get triggered or which layers get triggered, and so on. So this is really from a developer's perspective. An explanation is post hoc. It is after all the performance evaluation and doing all the tests, and it is ready to go. You look at its performance and see whether the results have been correct, to what extent, where it's failed. And again, that is from partly from a developer's perspective, but also from a user's perspective. Why was I charged why was I given a penalty notice? I did not drive fast on this road, is the question you might pop up. But what we would expect the system to say is, with specific reasons and specific evidences, valid reasons and valid evidences. So it's the simplest example I can think of. But we shouldn't allow tools to rule us. But then if you have to use it, it must be able to convince a user the need for it and that it does it right. So these are the two versions of the same concept. It's about whose perspective are we looking at in terms of explainability. So this one is a nice example. I just wanted to say that there are different types of uh, issues which can be handled. So if there are critical systems, such as a industrial plant being shut down, or that you may receive a penalty notice, then users get affected by that, and therefore we need to have some explanations for these things happening. And likewise, developers would like to address bias in their algorithms. If you don't have sufficient data for all classes that you're training, obviously there is an imbalance, and that might have a bias, might introduce your bias in systems. And also be able to rectify some of the mistakes in models. And this leads to the concept of moving from black box, which means we don't know what's happening inside, to a white box, which means it's more transparent. So on the right hand side, you see an example. So over here, on the left hand side, the first column is various techniques of AI. And over here, you have different objects that have been recognized. And let's look at this horse. It's got the highest recognition rate amongst close to some other, the top few recognition rates. You can see it's 80%. And then let's look at the image. We want to be able to understand how did it manage to recognize so with such accuracy as 80.45. So when you look at these heat maps, it kind of says the heat maps are the areas as key features that contributed to this high values. But if you look closely at the lower bottom of the figure, we can see this has got the highest heat map, and this actually corresponds to copyright information. So every time you produce a horse with this copyright information, I think it's losing the plot. It's not necessarily picking up information from the horse, but rather, sorry, but from this copyright. So this means that there is a flaw in the model, and this we need to, first of all, this needs to come through in order to understand there is a flaw in the model. And that's what XAI systems approach is. So that's about XAI in general. Now I want to jump to the actual application, which is the touchstroke biometrics. And we call it as the touchstroke dynamics because there's so much real-time continuous action that takes place when you swipe your mobile or any other mobile device. That our hands move, we apply pressure, we tap, we lift, we touch, and so on. So, how different people swipe differently to reach the same page or to look at the same image, and that becomes a trait and represents individuals and discriminates one from the other. So, that's what we are going to look at. So if you look at a biometric system, these are the standard blocks. So you have a user, you capture his biometric data, you build models, and then you make decisions correctly or incorrectly. So if you are able to interpret how the decisions were made, and you're able to identify the correct and incorrect classifications, and if you're able to feed that back into the system and change the model structure, adjust itself, then you will certainly improve the performance of the system. So that's from the developer's perspective. But if you look at the user's perspective, if the system is capable of providing some explanations, then you will be able to trust the system better because you see the reasoning behind a decision. And you may use your feedback as input to, as a user, his or her feedback can go back into the model refinement and improve its performance, but also is satisfied with simple and complete explanations, which in some cases can be documented, as in a medical diagnosis or in a law enforcement situation. So we can use these explanations for legal reasons and for satisfaction of users and so on. As I said before, so we have behavioral biometrics, which relates to having a mobile device. The device itself will have some sensors, such as the accelerometer or gyroscope, or even tapping the keyboard, not the soft keyboard, and the number of delete key, anything, any characteristics that come out of it can be used as features to describe the individual and stored. But also you can intermittently capture the such features from the user's behavior, and you would be able to dynamically authenticate a person. So this is kind of saying how often you sample the signals, and then you extract key features from that, and that goes as a labeled data set for every user. So that's the general principle, like in any AI system. So so this is typically used for continuous authentications where you might need, such as in the banking case, if you were to do some transactions, or in online exams and so on. So this would be ideal for real-time applications. So there are lots of tools actually. You don't need to, I mean, you still need to program, but then you don't need to start from scratch. So there are lots of XAI tools, but they vary in the type and accuracy and scalability based on the things that we do. So if you need a very high performance system and you're dealing with lots of data and you need to apply it at different scales, high scales, then you need explanations that are quick and efficient, and the algorithm itself should be capable of handling any increase in data or complexity. And also, depending upon the machine learning categories, there are different types of machine learning algorithms. So depending on, so here I've said, for example, whether it's deep learning or decision tree, they are two different types, and therefore the tools will also vary. And then the kind of outputs we want. What kind of outputs do we want? Do we want to do some visualization for developing it better, or for using it better, or for reporting it or documenting it for some specific purpose? So depending on that, XAI can have different types of tools for analysis and outputs. So there's a whole range of tools and frameworks. I haven't used any of these, but I just checked on what these are. But yeah, there are quite a few tools such as this, what we see here in the list. But I'm going to look or consider two tools for today's presentation, which has been used in this project. One is called as SHAP or Shapley Additive Explanations, and another one is called LIME, which is Local Interpretable Model Agnostic Explanations. So both provide explanations. SHAP will talk about how much does each feature contribute to the overall outcome by itself or in combination with other features. So a single feature by itself can make contributions to a particular output, or a feature in combination with one or more combination of features can still contribute to the same output. So you want to look at these possibilities and understand the importance of features in the outcome. Line says this is where the original definition in quotes works very well for Lime. Lime says, I actually don't care about the global output that the model produced, but I'm going to take an example, test example, and I'm going to perturb the feature values. I'm going to find feature values that are around or close by or in the neighborhood of this of this feature in feature set in the n-dimensional space, and perturb it, and then see what kind of output I get and whether I'm able to follow that, whether I'm able to understand that. So that's why it's called as a local interpretable model agnostic, meaning that it will work for any model that we develop and it provides explanation through that process. I'm not expecting you to read the text from here, but basically AI, there are lots of terminology. So we talk about responsible AI, we talk about explainable AI, conversational AI, and trustworthy AI. And they cover specific aspects or they can have overlapped aspects that they cover. So, for example, responsible AI would cover principles of being fair, transparent, explainable, and human-centered, as well as maintaining privacy and security. If you look at the trustworthy in the bottom quadrant, there are 6 pillars of trustworthiness, which is safety, security, privacy, reliability, business integrity, and resiliency. So these are terminologies that have overlaps, but ultimately they talk about explainable systems providing safety, security, reliability, etc. So I'm just going to spend a little bit of time on Lime and Shap. Those of you who want to fall asleep can easily do that. I won't complain about it at all. But I've tried not to go. This is like a very class-like sheet, a slide that you have to bear with me. So as I said, Lime, I'm going to read some of these bullet points. Lime wants to find out whether a model's output is faithfully following the local inputs as well. So as I said before, the any model will work around several hundred samples. But if you take one test sample, it's got its own features which could be aligned with the output from the model or not. Anything can happen. So this is about finding whether they are aligned or not. So we talk about local fidelity, which basically verifies how a model represents the features around a prediction. And this may not fit mostly, often, with the global fidelity. However, what it will show is that how the decision was made. And it focuses on addressing 3 trust areas: model trust, prediction trust, and data set trust. Do you trust your model? Do you trust your own predictions? And do you trust your data set? So these are the things that it will address. So here's a nice example on the right. So there's I don't know about these viruses, probably Nandakumar, you might be able to say there's a Chicago virus or something like that, which has got certain symptoms: high fever, mild sputum, mild headache, and so on. So these are typical symptoms for this kind of a virus. But there's the possibility that there is a prediction that was true, but then it had slightly different symptoms. Okay, so it could be a false positive. And therefore, how does the system pick that up and how does it rectify it? We need to have some insight in order to understand that this could lead to a false positive. So Lime will search the vicinity of the prediction to explain the decision the model made. So if there are slightly different symptoms, then Lime will step in to explain how the decision was made. So we are talking about local features and the importance of proximity in line because we are perturbing the features. We want to look at the proximity, nearby values. So if you look at the three statements that are made here, Line would typically look for these keywords. So the first statement actually refers to Saturday Night Fever. It's a movie, and therefore the keywords there are fever, Chicago, chills, and days. Now, all these words are common to the Chicago virus as well. So, this sentence might be mistakenly treated as having the Chicago virus. The second one, likewise, is talks about an actual situation in Chicago, mosquito bite and fever, which kind of points to the Chicago virus, and probably this would be a correct classification. And the last one says, I went to Italy, had a fever and difficult breathing. It kind of moves towards point two, but actually it could also be COVID 19 or anything else. So there is the ambiguity. So what these three statements indicate are that we need to be careful in terms of how they are classified. And this is where Lime would help to look at neighborhood points and features and be able to make a decision, be able to explain how the decision was made. So the bullet point in the end says Lime draws local samples to produce the best interpretation and explanation regardless of what the model says. So this is all about Lime. So Lime proves that even accurate predictions cannot be trusted without XAI. They work with local interpretable models. And the purpose is to measure to what extent we can trust the predictions. Local explanations show that the data set cannot be trusted to produce. So all these local explanations, the purpose of the local explanation is whether we can trust a prediction, whether we can trust the data set. And some of the visual explanation will actually help us to clear our concept as to how it is doing the explanations. So what do we do with these explanations? Okay, we have a system, we've got some tools that will give us some explanations. Then what do we do? So the next step really will be the user has an explanation that doesn't meet his expectations. So then why did I get this penalty? I didn't even go through that road. Then obviously there is something wrong with the system. So we need to investigate where the issue occurred and improve the model. And also, no conclusions can be made before investigating the causes of the explanation. So postpone your decision until you're sure what caused the decision and so on. So that's as far as Lime is concerned. So SHAP is another tool, and this was derived from based on game theory, and it relates to footballers as a very nice example. So it talks about coalition of players. When players come together, they contribute to scores, and the individual contribution and the permutation combination of coalitions, when you add them all up, it's much more than simply adding up the individual contribution. So the impact is far more when you look at, for example, features by themselves as well as features in combination with other features that might lead to a prediction. So the total value of looking at the contributions of individual features of footballers is superior when you compare to the sum of the individual scores. So this is where it talks about the marginal contribution of a feature to the model, but it does that not on the overall prediction, again on a include them in other games. So those complexities are nicely embedded mathematically through SHAP. So it is said that SHAP plays a fair mechanism for bonus distribution. That's the notion. So we talk about coalitions and marginal contributions. So if you had three players, A, B, C, and you want to find out what is the contribution of player C, then from the total contributions, you deduct the other two people's contributions, which is what you will get as the individual's contributions. So we talk about players, but in machine learning or AI development, they are nothing but the features. And this is what we call as the marginal contributions, but we look at all the possible combinations. Whether this feature exists or not is binary, and the number of combinations is n, therefore you have several possible combinations of 2 power. So values for each prediction represent the estimated effect of each feature, not only each feature, but also a proportion of the interaction the feature has with other features. So it's also like you and I joining together and doing some work, plus each of us doing the work individually. And if we repeated that with every other person in the room, what's the energy we generate, for example? So it'll be far superior. So these are the two tools that we are using in this application. So I wanted to look at understand the low-level data that comes from touch-stroke dynamics, so we understand some of the behavior which we hoped will be useful in the later stages. So that I call it as behavior analysis. So there are some licensed data sets that we used, and one of it uses two activities. One is reading material like Wikipedia, and another one is viewing images in a gallery. And then, so here you have in the first, there are two users, the user numbered as 8 and 22 here. And we can see their swipes, how they vary. The green and the pink are various swipes for the combined activities. And you can see the patterns are slightly or more than slightly vary. And then also how you hold your phone, whether you hold your phone in portrait mode or in landscape mode, that makes a difference. So on the second graph, you see the two user samples in portrait and landscape mode. It looks like the pink represents portrait mode and green landscape. Hardly any samples there in the landscape. So there was no restriction as to how you should handle the mobile device. So they would do a lot of activities. The only thing is they were forced to leave the phone or mobile and then device any mobile and then pick it up again. So sometimes we might place it in one angle, another time we might place it in different angle, and we may so it allows the natural manner by which people use mobile devices. So that's the setup. And so we can see that behaviors change. Now these are the trajectories of different users. So the green points represents the start and the red points represents the end. And both in portrait and landscape mode. We know that landscape doesn't have much data, so that's why you see very few swipes. But on the portrait, you can see quite a lot of swipes and angles and directions and points and so on. And if you this is for one user and this is for another user. So you can see how much how they were. Of course, I picked up one to show this discrimination, but maybe there are quite a few other users who are very similar to each other. But just to point out that different users could have different trajectories. So this is for portrait and this is for landscape. This one is interesting to see. I wonder what happened here, that it's all centered, it's all focused, or it's the mass is, the center of gravity is really at the end of it. So probably they're doing a swipe viewing gallery and so on. And then I'm sure all AI developers and researchers will know about confusion matrices, but here is a correlation matrix. So these are what you see on the bottom and on the right are various features derived from the sensor data. So typically you can determine the orientation of the device, the finger area, the touch points, and then and from that basic, the swipe duration, even the swipe duration is derived. So from those 4 or 5 input data, you can derive various velocities, the angles they make, and the curvature they make, the acceleration that's involved. So it all depends on geometry, time, and what else? Velocity, speeds, and things like time, basically. So different types of features can be extracted, and some of these are correlated one with the other. So what the heat maps say that one feature is positively correlated to another feature depending upon the intensity of the heat map, and the blue ones show negative correlation, which are equally important. So we can see there are some, for example, the x coordinate is doesn't seem to have any impact, but then y coordinate might, and pressure might, and velocities and swipe distances and so on. I know these fonts are small, but this is to talk about the data, how it looks, and what needs to be really pre-processed and be aware of. Um, okay, so that's why I call this as data science concepts, but it's common for any application. So one of the things is to remove bias. The whole idea of XAI is to remove bias, be trustworthy, and all that. So there's no point if you have a very biased data set. So in this is a different data set I was working on. So just to keep it brief, it was easy to plug this data in here. So it's not necessarily related to the actual results I have here. So here we got 6 devices and we got 5 users. There are some zeros. What that means is that on device 6, only one user had used device 6, the others didn't. And if you look at user 5, he or she has used only device ID 2 and not on the others. And of course, there's 4, the user 4 hasn't used device 3. So this will cause quite an imbalance in the data. So there are lots of ways to sort that out, but the shortcut was I simply got rid of this device and this user in the first instance. I'm not sure, I might have even removed, oh no, not necessary. And then looked at the minimum count across this pivotal table, and it was 1370. So kind of made that uniform across each device and user. And this one, I think we did some imputation, which is artificially creates data of 1370 using, because it's the same user on different devices, you could do that. So these are some mechanisms for, first of all, balancing the data. I'm jumping from the raw data to features, where after a few stages you extract the features. And if you did the whisker plot, you will see a few outliers. It's best to remove these features or points or samples from your data sets, simply because they may throw your decision badly. So they might contribute to an incorrect decision making. So keep an eye on outliers. And so that was the fundamental simple thing that we had to do, but also was an essential thing to do, because when we first did without doing any kind of cleaning, we deliberately did that to see what the performance looked like and how badly it affected the result. So classifier is a classifier which will learn but also be able to test various data sets. So we were using random forest, and I'm not going to take a lecture, but what this random forest in very simple term does is that it is able to make some division. It takes the data and applies a rule and splits them into branches of trees. And it is supposed to do that based on the best feature on the best fit. This is a very small example. You see numbers of zeros and ones, and first of all we want to divide the data by color. So you go by blue numbers and red numbers, you get 100 and whatever here. But also now you want to split it by the value, because it is only binary. You want to separate or split the tree as ones and zeros, so you get to this, and you can apply some conditions to get to the leaf of the tree. So it's very simple here, very simple example. But if you had hundreds of features, then this rule becomes very difficult. It's a hard problem, especially for any real world application. So what random forests do is they determine what's called as the Gini impurity that will enable the system to do the split based on the best feature and best split. So I'm not going to go into this mathematics, but although it is simple, that's not the purpose of this session. So we did the cleaning, we got the data, and of course we applied random forest as a classifier, and we can see that we actually have separated the data set into 23 different subsets, which I will come to later. But here I'm showing the results only for portrait and landscape mode of the mobile. Obviously, like in any other system, the performance of the system, one means is the best performance score for different sample sizes. You would find that during the learning phase, of course, the performance will be very high, but it's during the validation phase. This is called cross-validation results, where you have different shuffling of data sets and so on. So it shows that small sample sizes are not enough. You really need very high sample sizes to get anywhere close to one and so on. So our aim in this project is not about the performance of the system. It's about building explanation or providing explanation. So we have done done work on how to improve and all that, and how to build a system that gives really very high performance, but that would be overfitting and so on and so forth. So we are not going into that part of analyzing the performance of prediction accuracy. Rather, we are going to look at the explanation. But generally speaking, random forest is from the interested in bringing in all the other classifiers. So we can't say this is perfect, but we also wanted to show what can we do. Can we look at the feature importances? So random forest uses what is called as the mean decrease in impurity as a mechanism for determining feature importances. Basically, it's in random, it adds features to a set and it uses those features to do the learning and the classification. That's what this whole concept behind is a concept that it uses. So it's an inherent feature importance mechanism. So it tells us which features are most important. So if we trusted those importance of features, we can use it as ground truth to validate, align, and sharp results. So we have here the importance of different features for portrait and landscape mode of operations. So it's got swipe distance as the top feature for portrait, but here it says finger area is the key feature, the topmost key feature in landscape mode. So they don't necessarily have to be in the same order. However, it'll be nice to see that some of the features are in the top 10 ranks of the importance. So random forest feature importance by, as I said before, by adding a random feature to the existing list of features, random forest has ranked these features as the most important ones. So one drawback with the random forest feature importance is that if a feature has got a feature that has more categories or subdivisions will be treated as the top rank because it likes high cardinal values, and therefore that is one of the disadvantages of this feature importance mechanism. Anyway, that information is for by the way. And now I want to look at XAI techniques for feature importance. So we got this built-in feature. There's also another feature called permutation-based features, where we talked about which overcomes this the cardinality issues, and it uses a certain algorithm which is listed here, but I'm not going to go into those details. But still, this one will very much depend upon the feature importance relies on the model performance. If you have a very good model, if you have a very good classifier, then the feature importance will be different from a very poor classifier. So it's kind of depends on that. So when when with respect to features, because we are talking about feature importance, it's important to remember to normalize the feature values. So when you, from your raw data, you extract features. If you look closely, which we also did with our data, was that some ranges are in one end of the spectrum, and there are other features that go for a much larger range, and that is not useful, because then this will look insignificant. The smaller values will look insignificant compared to the larger range of features, and therefore it's important to normalize the features for computational purpose. So we did that for x and y coordinates. So then the x and, but then for visualization, you still need to bring them back to their normal values, so you understand and you can relate to the physical values better than using the normalized values. So that's another important point. So I've done some work here. So there are two different types of feature importance techniques we discussed now. One is the random forest MDI, and the other one is the permutation importance that I talked about later, last. And then considering the last 10 or the top 10 features, so these are the rankings, which the system is not on XAI, it's traditional techniques. You can see that some of the features are in this blue finger area is top, whereas the finger area is third from top. And then this 80% end-to-end deviation is second, and 80% deviation is on top here. And then 50% deviation end-to-end is at the bottom here. It hasn't ranked it as much as this one has done. There are some features that are present here, but not here, and vice versa, and so on. So this kind of gives a picture that when you look at any two different techniques, they don't really come together. So they will have their own ways of measuring, and therefore we need to be aware of that. But I also wanted to kind of project that onto the correlation matrix to see whether it makes sense that these features which are on the top have any correlation with any other feature. So if you look at the y coordinate here, so x and y coordinates have very light shades, so they don't really play much of a role, except for x coordinate with one of these features and so on. But pressure does. Pressure has some correlation, and it's not too high in the list here. And I'm not sure where pressure is too high in the list here. So you can draw these correlations and see what happens. This is your own data set, and therefore what do these systems say is the analysis that in order for us to even develop an XAI system, we need to have understanding of the basic data that comes from sensors and devices and so on. So this low level processing is important. That's the point that I'm trying to make. So the outputs for LIME and SHAP are as follows. So we have SHAP. It produces a summary plot. It has an X and Y axis, and it has got positive and negative values. So this is from a different example, not from the biometric data. So this is on diabetic data sets for detecting diabetes. So you can see that if the glucose, so on the right hand side, it's pink, it's positive, blue, negative. So a very high value of glucose content obviously it will lead to a positive prediction of diabetes. And that is what these are the features. So you can see how they are ranked, and their values are here, and it kind of makes sense. But this result is not on the entire data set. This is from from one sample, and that sample says that for that particular sample, this is how the importance is. And this is LIME. LIME also says something very similar, but the way this is arrived at is different. Here, it considers a test, but it also disturbs the test. It doesn't use that value as it is. It finds a neighboring point close to that feature vector, and then sees what happens to the results. So it says it kind of tallies with this. It says glucose value greater than 99, has diabetes, and blood pressure. A combination of these produces diabetes. So for that particular test case, it has. And there are other features that push it the other way around. So in AI, all features don't come together. Some features will move the result in the right direction. The, the others will move towards some other class, to some other incorrect classification. So these values move towards some other classification, and likewise all the blue ones pull towards another classification. So this is the main concept behind SHAP and LINE. So what we did was, we did have the classifier results, and we wanted to analyze what's happening to our own data. We did several, probably nearly about 30 or 40 different samples we have tested, and we've arrived at this LIME and SHAP results. So this is a case of correct classification where the predicted user and the actual user are one and the same. The user meaning here the subject. So we looked at the line explanations and at SHAP explanations. I just checked swipe velocity is top, and this is comes second. Pressure, any value. This pressure is moving it in a negative direction. Pressure greater than 0.58 actually moves it to not belonging to this class. And here pressure is also in the negative direction, so it's again pulling it away uh, from uh, from this class 19. So we can see that. So in this particular example, they both seem to coincide in their kind of decision. So we can come up with some conclusions to say, oh, okay, we got these features. So let's look at the positive features. These are the rankings. And let's look at SHAP, and maybe there is a consensus or maybe not. But the tricky part is when we have a misclassification. So we got the true user is 54, but the predicted user is 30. So we see swipe velocity here at the top, and then swipe velocity is actually in the opposite direction. And then we got this 50% pairwise accuracy and the pressure pulling the system towards a misclassification. And again, they are pulling them away from misclassification. So it seems on this occasion, they seem to kind of come together, but that is not necessarily true in several of the other the test samples, whether it is correct classification or incorrect classification. So this is the stage we are. We are now looking at the consensus of how we can rope this information along with all the previous feature importance measures and be able to provide proper explanations and incorporate into the model. So that is the question to ask. So I want to say at this point that there were 4 licensed databases, and we also generated these licensed databases were so disparate. They had their own different sessions, and then there were, as you saw from the data set, some devices had data, some didn't, some users did, and some users didn't. So it was quite all over the place. Therefore, we decided to generate our own data sets. They were generated as student project from Multimedia University, actually, and it's online, I think, and they are available through license if anybody wants to use it. So anyway, so we had these as the data sets, and I said, as I mentioned before, there were 23 different categories of data partitions and several different models. But in here, I'm just talking about random forest. But any conclusive analysis, arriving at any conclusion or analysis as a result of those or conclusions from the analysis has been very hard. So this by itself needs a consensus mechanism, probably using AI or fuzzy. So I've done some previous work on multimodal information processing in computer vision techniques. So maybe there are some concepts that we can bring together and see how we can integrate that information. In the end, we should have some proper explanations that will feed into the system for better performance improvement and probably better user interaction as well. So this is the stage that we are. So I don't have concrete results to say we did fabulously well or anything, but this is the stage. So from the data sets that we generated, we published through papers, and I think they are being now reviewed for journal inclusion. So in this work, as such, touchstroke dynamics is a new area. Not many people have worked in that area. And XAI is also an emerging area. So the combination of these two has been a very valuable experience, mainly because touchstroke dynamics is never used as a single modality. You can't trust that system by itself. It needs to work with password, or it could be part of a signature analysis, something like that. So by itself is not the best thing, best what do you call biometric system. So in a way, it is good to understand why that is the case, and if we can improve or add another modality, biometric modality to it, would that help? And these are some of the questions that we can answer. So that is it from my side. Thank you. Can you stop sharing?
Excellent presentation, ma'am.
Thank you.
It's really opened our eyes. We didn't think in this line.
Uh-huh.
No, it's new arena for us.
Okay.
Even for our faculty team, some of them are working on biometrics.
Yes.
They were working on gene expressions.
Yes.
They can think about this line also.
Oh, yes.
This is a
Definitely.
different zone for them to
Yeah.
understand. It's
Yeah.
actually really an eye-opening session for all of us. Surely you're going to have followers from our own department.
Fantastic. I'll be more than happy to maybe collaborate, and then I'll be very happy if there are some couple of questions if needed. I'm happy to answer as well.
Sure, ma'am. Some of them may be asking questions.
Even if you can read,
Scholars, scholars, if there is any questions, please you can ask.
you can either text or ask.
The virtual floor is now open for questions. Please type the questions or use the microphone to ask questions.
So there's no pressure to ask questions. I'm quite happy to leave it, and I'm quite happy for you to text any questions later on, or I'm happy to address later on. So, yeah, I'm quite conscious of your time, but I'm very happy to take now or later. Don't, yeah,
Surely we'll share the questions to address it again, ma'am.
sure. Thank you.
Thank you,
Thank
ma'am.
you. Can I stop sharing? Yeah. Yeah, I
Cheryl?
think. Yeah. No, I'm not sharing. I've stopped, I think.
Yes, ma'am.
So is that okay, Chandra? Can I leave?
Uh, Cheryl, please thank.
Okay, ma'am. Professor Dr. Soodamani Ramalingam, ma'am, we are deeply grateful for your captivating and thought-provoking keynote address. Your unparalleled expertise in artificial intelligence has not only enlightened us, but also ignited a sense of responsibility and curiosity within each of us. Your comprehensive understanding of AI's intricacies and complexities has underscored the significance of balancing innovation with ethical considerations. Your dedication to advanced technology in a socially responsible manner serves as a shining example for us. Moreover, your tireless efforts to inspire and educate the next generation of innovators are truly commendable. By sharing your wealth of knowledge and experience, you empower young minds to approach AI's challenges and opportunities with creativity, critical thinking, and a deep sense of purpose. Your valuable insights have reminded us that AI's potential extends far beyond technological advancements, holding the power to transform lives, communities, and societies. Your contributions are instrumental in shaping a brighter, more innovative future. Thank you once again, ma'am, for illuminating the knowledge about SHAP and Lyme. emphasizing the importance of responsible explainable AI and about biometrics with explainable AI, guiding us towards a more sustainable and equitable technological future. We are honored to have had the privilege of learning from your expertise and vision. Your legacy will undoubtedly continue to inspire and motivate us to strive for excellence in AI research and applications. Thank you once again, ma'am.
Thank you, Ms. Cheryl. Thanks a lot. My pleasure. Thank you.
Thank you, ma'am. Thank you, ma'am.
Oh, my pleasure. And all the best.
Thank you.
With the insightful sessions we have had today, covering topics from AI to biometrics innovation, we can truly appreciate the strides being made in advanced computing. We would like to extend our heartfelt thanks to all the distinguished speakers and participants for their valuable contributions. As we draw the curtain on the first day of International Conference on Advanced Computing, we encourage you to join us tomorrow for more groundbreaking discussions on AI and ML in healthcare, data governance, and much more. We look forward to another day of rich discourse and innovation. Have a restful evening, and we will see you tomorrow for an equally engaging day two of ICAC 2024. Thank you.